Okay, so we finished up the lab where we looked at temperature inside a bottle and how it changes when we have a change in pressure. So we looked at how we can make the cloud in the bottle, and what happens is when we squeeze the bottle we have the warm air holding more water vapor than the cold air, and when the pressure is increased we see the temperature goes up, and we talked a little bit about Boyle's law and Charles' law. Okay, and this causes evaporation to take place inside the bottle. The warmer air inside the bottle holds more water vapor until you let go of the bottle, and this causes the temperature to go back down to a special point which we call the dew point, and that water vapor is going to change back from a gas to a liquid, which we call condensation, which is going to give off a little bit of heat energy as well. As that water vapor drops, it's going to stick to what we call condensation nuclei, or in the example in our lab we added the matches which gave off some smoke. Okay, and here's a little video of how we made the cloud in the bottle. We're going to add a little bit of water to the bottle. By adding a little bit of water, we're going to then shake that around a little bit, and that'll give us a little bit more water vapor in the air. So as we swirl around there, we'll get a little bit more water vapor in the air, kind of get it all over the surface of the bottle, allow it to kind of shake around a little bit. Then we're going to add a little condensation nuclei, and in this case our condensation nuclei is going to come from smoke that we get from a match. So we light the match, we drop that into our bottle, and when we drop it into the bottle we put the lid back on. We want to capture as much of that smoke inside the bottle and keep it in there so that the water vapor has something to stick to. Now when we squeeze the bottle, it will trap the smoke inside there. When we squeeze the bottle, it's going to raise the temperature inside, or if we add more air molecules to that bottle, it's going to add to the temperature inside. That's going to allow more evaporation to take place, and warm water or warm air can hold on to more water vapor. And if we get that warm air in there holding more water vapor, when we drop the temperature back down, it's going to drop back down to the dew point, and we're going to then get the cloud to form. So now we're going to release some of that pressure. It's going to cool down the air inside, and we get a cloud to form inside the bottle. If we warm the air back up, we can get that cloud to disappear, and we'll get that water vapor to go back into the air. And then we can cool it off again, and we can keep getting that cloud to form and go away, and to form and go away. So right there we warm the air back up inside. The water vapor evaporates again and gets back into the air, and then we're going to cool it back down, and we can get that condensation to take place again, and the cloud will form. Okay, now we can look at how a cloud forms in real life. So we're going to take that same idea of the cloud forming a bottle, and we're going to now add into that the different environmental factors. So the first thing that we're going to look at is the surface of the earth. Like we said before, warm air is going to hold more water vapor than cold air, and to get that we're going to have the sun heat up the earth. As the sun heats up the earth, it's also going to cause the air to warm up, and evaporation will take place. And with evaporation taking place, we can change liquid water into water vapor. So we get these water molecules here, we add enough energy to them, they start moving around, get excited, and eventually they break the bonds holding them, and they can then enter in as an atmospheric gas. We can then have that warm air, lighter and less dense air, rise up. As the warm air rises, it is going to start to cool off. Every 1,000 feet that it rises up, it's going to cool off 5.5 degrees. So as that warm air rises, it's going to keep cooling, and eventually it's going to reach the dew point, and that's when it's going to stop rising. We can see here in the little diagram, we have our surface temperature and our dew point. We have that warm air rising, and notice that it keeps cooling here, and eventually it will rise a little bit more, and then eventually it will cool and reach the same temperature as the dew point, and that's where we have our cloud form. Okay, the dew point is not always the same, and with different dew points on different days we're going to get different types of clouds, or possibly no clouds at all. So we really have to make sure we understand that the dew point is not always a specific temperature. It's going to vary from day to day, and that's what's going to give us a lot of the changes that we get in weather. Now for the actual forming of the cloud, once we get up to the dew point, the cloud is going to form. It's going to have condensation take place, which is going to give off heat. Then the water molecules are going to stick to that condensation nuclei. Condensation nuclei, one of the vocab words that we had, it could be dirt, dust, or like in our lab we use the smoke. It could be pollen, bacteria, anything that's going to give the surface, going to give a surface for water droplets to stick to. And as more condensation takes place, that cloud is going to grow larger. I have a little diagram to kind of give an idea of the size of the water molecules in the air compared to the condensation nuclei. We're looking at these water droplets. They're very, very, very tiny. That's why they can fit in the air. They're all around us. We just can't see them because they are that small. The condensation nuclei is also very, very small, but it is 10,000 times larger than the water droplets themselves. So that's why the water droplets and the condensation nuclei can fit in the air. These are very tiny things, but when they kind of group up, they can get very, very large and form a cloud. Now we looked at why don't clouds just fall out of the sky? And the reason is buoyancy. Because the process of condensation gives off heat, which is an important thing to remember, it's going to warm the cloud just a little bit. And going back to our conversation on density, cooler things are going to sink and they're going to be a little bit denser, and warmer things are going to be able to be lighter and less dense and float on top of cooler, denser objects. So the air gets a little bit cooler at those temperatures when we reach the dew point, and it allows the cloud to float or sit on top of that cooler, denser air because of that little bit of heat given off by condensation. Okay, and that's how the clouds form. The last thing that we looked at were the different types of clouds. We looked at just kind of the four main types of clouds, or we call them the core clouds. Our cirroform clouds, cumuloform clouds, stratoform clouds, nimboform clouds. So starting off with our first one, it's going to be our cirrus-style clouds. All these different clouds can combine and come together, and they could form many different types of clouds and combinations and variations on these four basic clouds. But cirrus clouds are going to be high upper-level atmosphere clouds, hair-like, okay, wispy ice clouds. Cumulus clouds are going to be our next type. Cumulus clouds are going to form from rising mounds or domes or towers with bulges on the top parts, often resembling a piece of cauliflower, or a better example I feel is they kind of look like white puffy cotton balls. They're always going to be flat on the bottom, so like we talked about with that change in density, we can see in this picture very, very well that that change in temperature allows these clouds to sit on top of that colder, denser air. Okay, but those would be our cumulus clouds. Then we have our next type, our stratus clouds. Generally gray clouds. They form layers, very, very uniform bases. They're broad, wide clouds, like a blanket. You can see very, very flat and stretched out clouds. And our last type, our nimbus clouds. Nimbus, again, is the Latin word for rain. These are going to be our rain clouds. Nimbus clouds are not going to be able to stand on their own. They're always going to be like a cumulonimbus cloud or a stratonimbus cloud or some combination of a different cloud type and a nimbus cloud. Right here I have a picture of a cumulonimbus cloud. These are your thunderstorm clouds. This is probably the easiest example of what a nimbus cloud would be, or our best example. When we think about heavy rains and lightning and thunder, and they're going to come from our nimbus clouds again. Okay, a couple other little things that we've looked at this section. We did talk about Charles' law. So here's our definition of Charles' law. Okay, an example of how gases want to expand when heated. So when we look at Charles' law, we're going to look at gases under constant pressure, and their volume is going to be proportional to their temperature. And what we're going to see is as we heat things up, they're going to want to expand, and as we cool things down, they're going to want to shrink. Okay, we have our animated cartoon here of what Charles' law kind of works out to be, and we can see here in the first one that they're all kind of the same. And we have here in the second part, as we change the volume, the temperature is going to go up as well. And here, when the temperature goes up, so does volume in the last one. So we have our little cartoon of Charles' law there, and showing the relationship between temperature and volume. And again, just to review, we have our vocabulary words for Investigation 6 vocabulary here. We have cloud, condensation, condensation nuclei, cuneiform, dew point, evaporation, humidity, precipitation, saturation, stratiform, transpiration, and water vapor. So we look at some cloud types there. We're looking at some words dealing with the formation of clouds. If you guys can, when studying, work on how clouds form, we're dealing with evaporation, condensation, dew point, humidity, all those different terms that are going to be on the test. If you have any other questions, feel free to ask before we start the test. Otherwise, good luck.